Hi, my name is Jonathan Savis, and today I'll be presenting the Enpiction application. So Enpiction is an app to hide secret data across groups of images using Steganography. This adds a layer of security over a centralized data store, such as a mobile device password manager. So the methodology here is we'll prefix the secret data for each group with a UUID unique identifier, and then the size of the group so that we can authenticate data retrievals. We'll encrypt using a GCM block cipher and the AES algorithm. GCM uses an initialization vector, which is more secure than other modes such as ECB. GCM also authenticates the data using MAC so that we can determine if data we are retrieving has been corrupted. The steganography algorithm uses a least significant bit embedding technique to hide the data within the image, which we'll see next. And finally, to make the process inconspicuous, we'll overwrite the existing images so we do not produce duplicates. In addition, we'll retain the last modified and last accessed metadata for the files so we don't leak information about the image groups. So PNG images use a lossless compression algorithm, which means that when we compress and decompress the data, it remains exactly the same. This means we can work directly with the image pixels in a bitmap. Pixels are represented as 32-bit groups with channels representing red, green, and blue. The fourth represents opaqueness, but we won't use that for the embedding algorithm. So as we can see, we'll iterate over the RGB channels of the pixels, grabbing 2 bits at a time from the text and setting them as the lowest 2 bits of each channel, where they will make unnoticeable changes to the image. To retrieve the data, we reverse this process, grabbing the lowest 2 bits of the channels and rebuilding the message bytes. JPEG images use a lossy compression type. Compressing a bitmap to a JPEG and then decompressing back to a bitmap will result in data loss, so we can't use the bitmap to hide our data. There's 2 parts to the JPEG compression. The first is the lossy part, which compresses the bitmap blocks to blocks of 64 DCT coefficients. From here, compression to a byte stream is lossless, so we can manipulate the coefficients. So what we do here is hide 1 bit per block of 64 coefficients in the least significant bit of one of the coefficients, in this case index 1. From here we decompress to the DCT coefficients instead of the bitmap to rebuild the message bytes. So these are some links to some demo videos, but we'll do a live demo here. So we'll go encrypt and we'll choose some images. So as you can see here, we'll use the example of storing a Facebook password. So maybe we want to say that this is for facebook.com. Well, then we'll add an image, and then we'll use this Facebook screenshot to store our password or username. We'll add one more image, and just for fun, we'll store the password in a picture of me. And we'll make this our Facebook password. And then we'll encrypt. We want to encrypt 3 entries, and we'll enter a key. We'll say it's AES. And it goes through and encrypts, and it's complete. So then when we want to go decrypt, it's a similar process. We'll grab these 3 images where we know they are. As we can see here, this is a limitation we'll talk about later, but the file size of this JPEG grew about, maybe it was 2 to 3 times larger. That's a function of changing the bits, and it doesn't compress as well. So we'll enter our key, and we'll decrypt, and we'll get our messages. There's our password, there's the website, and there's the username. So one function is that we have to choose exactly the 3 images from our group. So if we choose 2 and enter the correct key, even though those are in the same group, it'll fail. And this is to prevent people from just brute forcing their way through all the images. So in conclusion, decentralizing the data by distributing it across images in the file system makes it harder to find the data, but of course fetching data in this manner is less convenient than a password manager application. The size of the data we can hide is limited by the size of the image, and the max message size, including the metadata that's appended to Enpiction, is about 200 characters. So this is almost always not an issue, but for very simple JPEG images, this is a potential problem. We can make improvements by using only byte arrays so that we can overwrite them from memory when we're done. We can also add support against timing attacks, in which an attacker could determine if some portion of the attempted key or the IV, or in the case of Enpiction, some portion of the image group is correct. And finally, we need to work out a way to reduce the image expansion. Here are some references to some of the code that I used to build the application. Here's a link to my GitHub. So thanks for watching.